Yes, that's Howard Johnson.
There's a photo of Johnson.
Yeah, this is the kind of build-ups that he did a lot of playing with little cars to propel them down the tracks, because he could set them to run past assemblies, and he could build magnetic assemblies in them, and he didn't always have to have a rotor thing. So he did a lot of things of running down tracks and running them around tracks to try to work out when this is an assembly, for example, where he's trying to set up a continuing series of all, as the little car comes by with its magnets, these magnets at an angle are steadily firing exchange force pulses. So this thing is, the intention is for it to come by here and get a steady series of kicks on through this gating area. And, you know, he had some success with that. He eventually could get a car to run round and round on the track and keep going. The big problem was the precision with which all this has to be made. It's something that a university could do, or anybody else would put their mind to it, if they would use the precision, if they would turn the young guys loose and let them go and say it ain't perpetual motion, it's okay, go ahead and do it. So any dipole, including a magnetic dipole, is producing an energy flow. It's like a river. There's a steady state energy flow coming out of that dipole. So the problem is, how do you use a steady state energy flow? That's the whole problem. There's no problem in getting the flow of energy from the vacuum. We don't have to rediscover how to extract energy from the vacuum. Charges already do that. Any dipolarity does that and puts out a steady stream of energy. So your question is, what we call a static field, how do I use a static field? And what he was wanting you to see is that he was putting these pulsars all around underneath what's going to run around it, or what's going to run on the track, or whichever, whether he's using a rotating device like a spindle, or whether he's using a track. And the others were different kinds of gates that he was experimenting with. That's what he's wanting to see here. He built the most, over the years and years and years, he built the most astounding sets of complicated nonlinear magnetic assembly build-ups you ever heard of. These are definitely not magnetic, standard type magnetic motor stuff. And he's after the exchange force. Johnson is specifically after that exchange force. He wants to get a pulse of energy that momentarily is about 400 to 500 times as strong as that magnetic field from that magnet, just for a little quick pulse. And he did do it a couple of times. By the way, after that one that he brought down here to Huntsville when I lived near the house and I played with in my kitchen, on my kitchen table so long, T. Henry had a process where you could go out to quartzite sand, good quartzite sand, these magnetic assemblies, and you could dig yourself up a ton of quartzite sand. $150,000 to $200,000 worth of magnets and magnet assemblies. Only one thing they took that little turntable. So they knew exactly what they were after when they went in there. He was working in spin flipping the spins. And today, of course, we've got a name for that. We call it spintronics, but it hadn't even been born yet as far as a separate discipline. Yeah. But he found the work in material sciences where when you flip the spins, you know, you can change the field. And he immediately said, if I can have two permanent magnet assemblies, and we're coming in here, let's say with a north and south pole attracting. This assembly is a north and this is a south. And as we're coming in here on our rotor, if I can have these magnets just so that as they get very close to each other and influence each other, one of them flips spins and becomes the opposite polarity, he just flips its polarity, then I'll be attracted in here and I'll be repelled out here. In other words, I'll eliminate my back MMF. See, normally I get attracted in here and I'm gaining acceleration all the time. Boy, I'm getting my shaft turning and cranked and accelerating, powering my load. But the moment I start over here, if I just did nothing else, I'd have to pay back every bit of that. I wouldn't have gained anything in a perfect machine. And with little losses and air drag and so forth, I can never get back out what I put in. So if all I do is consider polarities, if I consider north and south poles, I'm lost to begin with. You're not, you know, you've got a symmetrical situation, you're never going to get asymmetrical power out of it. So Johnson's basic approach was, I have to get this system to cause itself to become asymmetric. Pow, like that. And if I do that, the system can propel itself It is not a perpetual motion with no energy input, because we know from physics that any dipole has a continuing input of virtual energy from it. In fact, it is a broken symmetry, and so recognized in physics, any opposite poles, opposite charges. So he was on very solid ground in everything he was talking about 40, 50 years ago. The way he was thinking was very solid, very technically straight. Johnson's also got quite a background. A lot of people don't know. Johnson is a silencer expert. He did some very peculiar work for some very peculiar people. He got some patents on silencers. He once had the job of silencing a chainsaw, so that 12 feet from the chainsaw in the same room with it, you couldn't hear it running, the motor. He did that successfully. He once had the job of silencing a diesel locomotive. He did that successfully. So Johnson's got quite a few things that he's worked on, and he did a lot of stuff on magnetic brakes, stuff like that. So he worked on some pretty good magnetics projects way back there. But he particularly, a big thing and experience for me in working with Johnson made a profound impression on me on how important it was to read past just electrodynamics of magnets and read into magnetic materials and all the effects that you get in there, because there's something like 200 named effects. Only about 100 of them are well understood. And I didn't really realize that until I met Howard Johnson. And he made me aware there were all kinds of effects in magnetic materials and all that I had never heard of, never studied at all in anything I'd had. And sure enough, if you start in with the magnetics materials books, you run into all these effects that, my goodness, why didn't they teach me that when I was in university? I might have done something with it. But today, the thing about flipping spins is well known, well established, lots of papers in the literature, and they're now beginning to really work on it. As far as I know, none of them are trying to get permanent magnet assemblies to do their own spin flipping, but it's certainly going to occur to somebody sooner or later. That's what Howard does. The problem with the method that he had all these years, he did make successfully self-rotating assemblies. But the problem was that the precision with which you had to cut these magnets was so great that you got to have everything professionally machined, and he was trying to do a lot of stuff on a diamond saw. You'll cut 50 assemblies before you get one that's right that way. Whereas if you can stay on it with precision and work your way into what's actually got to be done, 4 or 5 build-ups, you can get in there to where exactly what kind of shape and configuration it's got to be. The other problem is you've got to have precision magnets. Just normal old magnets, they vary so much in the way they make them until, you've got to check your magnets pretty good, because they will vary from strength and a little bit off in direction and everything else between two of the supposedly same type of magnet. So you've got to give some what we would call quality control. But the precision of engineering of it is the real thing that is the reason why you can't just normally whip up a permanent magnet motor. But I did personally play with a successful self-rotating motor that he built. Absolutely nothing there but permanent magnets, no switches, no coils, no batteries, no wires, no nothing. And just sat right there and kicked itself around and around and around. But what it had was a successful set of assemblies that did precisely what he was talking about. As it came in here, attracting here with the overall north and south pole, the moment it got here, one of them flipped its spins. It caused it to flip its spin, and it repelled out the other side. So, and today we know that, that's founded. That's got good scientific foundation. There's nothing wrong with that. The only thing is, if you want to get where the extra energy comes from once it self-rotates and not be called a perpetual motion nut or something, you've got to show that what you really have is, very precisely, is a non-equilibrium steady-state system, which means there's a steady-state input of energy to your system. Well, with the broken symmetry of opposite charges, a pole is just a magnetic charge, we now have the proof that a magnetic dipole does, in fact, take energy, virtual energy from the vacuum, and does put it out as observable energy. In proper terminology, in thermodynamics, it has to be a non-equilibrium steady state, call that NES, non-equilibrium steady state system. You're not building something that mysteriously creates energy out of nothing. You're building something that takes hopefully a known or demonstrable energy source, has a steady input of energy there, converts it in form to be used by the system you're using, and then furnishes the output. It's really no different in concept, basic concept, than a water wheel sticking in a river. As long as that river flows and gives you extra energy, you can turn the shaft of that water wheel and you don't have to crank it. But now if you don't convert the river flow to rotary motion, if you don't do that successfully, if you just stick an average wheel with no panes, no directions, no nothing in there, you stick in there, it won't rotate and it won't power your generator. You have to have that control of the direction that it takes out, and it's got to be additive.
Is there a moment of transience as the poles shift, as the spin flips?
Yes, there's a little bitty moment. It'll depend on the particular assembly and everything. Some of them will spike pretty good. When they make there be a sharp spike is all you'll see. But that's fine, because we measured one of his, a set of his gates. Ken Moore, I hope you meet tomorrow, did the actual measurements on the bench with good force meters and everything, and we showed that you actually do get, he was actually able to get those sudden spikes of opposing forces. Now, that one we were measuring, instead of changing the whole polarity, what it would do, it would give you a sudden spike of opposite polarity momentarily. But you see, if you look at it as a conservative field, which means if you integrate it all around the loop, the line integral of the force all the way around this loop with any kind of normal magnetic assembly would give you a zero integral. A perfect system could not produce any more out than you put in. You would get it all in rotation here and pay every bit of it back in drag here in the back MF, and so the system would not continue to, a little air drag, little friction in the bearings, and it'll slow down, stop. You can give it a spin and it'll make a flip or two and stop. But if it is a NES system, if you're getting a steady input of energy that does get converted, and you can get it in pulses, you don't have to get it as a continuous flow. So what he was doing as he got over here, he would get a sudden spin flip which would create momentarily. By the way, that's called the exchange force. It's known. Feynman discusses it in his 3 volumes of physics, even that far back. Any good magnetic materials science book will discuss adequately exchange forces. And the exchange force can momentarily be hundreds of times stronger than the normal magnetic field of that magnetic assembly. So you can get a very powerful spike if you get everything just right. It's very short, so its time integral doesn't give you a lot of propulsion, but it gives you enough extra free propulsion that you no longer have a conservative field. The total line integral around the loop is no longer zero. Doesn't have to be. You haven't violated thermodynamics, haven't violated any conservation laws, haven't violated any law of physics, if you understand that every dipole is already emitting energy that's being taken from the vacuum. Now, if you don't have that in your model, then mysteriously this thing will seem to have created energy. And of course, all the forerunners, all the older guys in electrodynamics have all taken that attitude, because when they all started, there was no such thing as an active vacuum. Most of particle physics hadn't even been born. They hadn't even discovered the electron yet. So it was obvious to the most casual observer, as far as they're concerned, you couldn't violate that conservative field.
Tom, just to clarify, on spin flipping, what is spinning and what is flipping?
Okay, we have with every charge, like an electron, we have a magnetic spin, angular momentum. It really is a spin, but and the most fundamental thing in nature seems to be angular momentum. It's not really energy. It's angular momentum. They call it also action. And all of this other stuff springs from deeper studies in conservation of angular momentum and so forth. They can show that the conservation laws fall out of this. You get energy conservation, all the other stuff. So you're always worried about your angular momentum and everything's got an angular momentum, everything's spinning. It's a little peculiar, because if you really want to consider it as a spinning object, then it spins 720 degrees instead of 360. It spins one time in one kind of domain, it spins another 360 in the other domain, and starts over again. So you're a little surprised to find out that it's a little bit different from a spinning wheel, but it is spin and it is real, and it is angular momentum, and it is usable. So every charge has also its own spin, and they classify the whole particles by spin, and of course Dave can fill you in very adequately on that. So they study whole classes of particles with this spin or that spin and so forth. But spin is absolutely fundamental in physics, and if you do anything which affects those spins or flips their orientation, you now have energy available to you. It's called exchange force there. The application today that people are struggling with is called spintronics, and of course they're starting with semiconductors and a lot of small experiments, but they're getting there. They're getting some very nice, very interesting effects. But anybody's interested in magnetics, the biggest thing I could do to urge real quick is get yourself some leading magnetic materials textbooks, real good ones, recognized by experts. Get yourself 2 or 3 of those and really study those books, because you'll find all kinds of magnetic effects you never thought about even existing. And then when one turns you on and you say, hey, I could make a motor with that, if I could get the materials to do that for me, then take that one and do some research. And that's what Johnson did. And these were some of the build-ups that Johnson made, some of the incredible arrays of gates and getting these thrusters. And as you can see, his biggest problem in the whole thing was, for years and years, he couldn't afford all this high-priced precision machining. So he's working now where he does have access to precision machining, and I'm expecting some real beautiful developments out of Howard Johnson. I would like to see that. Howard is, of course, way up there in age. He's been a very stalwart researcher for many, many years, and I really would like to see him completely successful, while he's still alive. He's a great person, by the way. I might add that too. Thank you.